Hello and welcome, and today's video is all about substitution, which is honestly my favorite way of evaluating integrals. So, I think the most important question to ask is how would we integrate a function such as 2x square root of 1 plus x squared? Well, the issue is we don't really have a way of simplifying this function to make it integrable. So what we have to do is we have to devise a new method. And this method specifically comes from the chain rule. So you might recall that the chain rule says that if you have a f of g of x, and you're taking the derivative of that, then it's going to be equal to f prime of g of x times by g prime of x. And really what the substitution rule does, or u sub does, is it's going to be the inverse for the chain rule. It's going to be how we evaluate functions with the chain rule. So we say, or the substitution rule for indefinite integrals is if u is equal to g of x, then f of g of x times by g prime of x, you can clearly see that we have like the chain rule derivative part here, is equal to the integral of f u times by the differential du. So I'm going to talk a bit more about this differential du in a moment. But for right now, let's get started with evaluating an integral. So here we have our outside function and our inside function. So we're going to say u is equal to 2x. But now we have to find the differential du in order for our substitution to take place. As if we were just to put this u in here, we'd be integrating cosine of u, but with respect to x. For laters, we're going to show, or for reasons we are going to show much later on, we can't do that. So what we're going to do is we're going to find a way to find du. And whenever we were learning about differentials, we learned that maybe we can take the derivative with respect to x of u. So we're going to get du dx is equal to 2. Now what you have to do is you have to multiply the dx over, and we get 2 dx. Well, now we have our du, but we don't have a 2 to sub in for. So what we're going to do is we're going to just generate one. We're going to say that we're going to multiply by 2, but we're also going to divide by 2. So now we can do the u sub like we were intending to. So this function, or this integral, is going to become 1/2 the integral of cosine of u times by the differential du. Alrighty. Well, now that we have this, what is the integral of cosine? Cosine of u with respect to u. Well, it's going to be the sine of u. Well, we know u is equal to 2x, so our final step is finally getting things back in terms of x's. And then finally adding our constant c. And this right here is our integral. Alrighty, for this next function, and what we really want to start by looking for is, do we have a function inside of a function that we can see the derivative of somewhere else in this problem? And I think if you take a moment here, you might be able to see that the derivative of x squared is going to be 2x. So what we're going to do is, we're going to say our u, or the inside function, is going to be negative x squared. So then our differential du dx is going to be negative 2x. Solving for now just du, we get negative 2x dx. But you may notice, once again, we do not have a negative 2x. We just have x. So we're just going to add in a negative 2 and multiply the integral by a negative 1/2. And that keeps it equivalent. Now we can just sub in, or do our u sub, so we get u, or e to the u squared, or sorry, just e to the u du. We know that e to the x is our favorite function here because its integral is just e to the x. So we get 1/2 e, our u is negative x squared plus the constant of integration c. Alrighty, for this next one, I think trig substitutions are honestly a bit more difficult to see sometimes. So let's think. Well, with the sine, we have sine squared of theta, and the derivative of sine is cosine. So let's use sine as our u. So u is going to be sine of theta. Our du then will be cosine of theta. And I'm going to say that I'm just going to multiply the dx over in one step here. So I'm just going to get cosine of theta dx. Or sorry, d theta. There we go. So we're now going to get the integral of, we know sine is u squared, and the cosine of theta and the d theta just becomes a du. So now all we are left with is the integral of u squared. We can use the inverse power rule, so we get 1/3 u cubed plus c. U is sine of theta, so we get 1/3 sine cubed of theta plus c. Alrighty, give me one. Okay, now that I fixed everything here, we've got some more problems. In this next problem, we have a denominator that's degree is 1 higher than the numerator. So we can, and because we just have the function here, x to the 4th, we know its derivative is going to be x cubed. Times by 4, of course, but we're going to try and get that times by 4 in a moment. So we're going to say our u is going to be x to the 4th minus 5. And the reason for that is we want to try and make this denominator as simple as possible. So then our du is going to be 4x cubed. And the derivative of a constant is 0. So we just have to add in a 4. Add in a 4 if it will let me. There we go, 1/4, and then divide by 4. Now we can use our substitution, and we will get the integral of 1/u. As we just had to say that x to the 4th minus 5 is our u, and we're integrating with respect to u. We know that this is going to be the natural log of the absolute value of u, which in this case is x to the 4th minus 5, plus our constant c. Alrighty, for this next integral, once again, I think we can see that inside of here, we have a u. So our u is going to be x squared, and we can see that the du is here on the outside, the x. So our u is x squared, and then our derivative of u is going to be 2x times, and then the differential of that is going to be 2 dx. Now we just have to multiply by 2 to get the, so we can sub in du, and then multiply by 1/2 to make it equivalent. Alright, now evaluating, we get the 1/2, the integral of the square root of, and you know what? Actually, I think I might have done a small bit of an incorrect substitution here. I want to make this just a small bit broader. That's okay, we always make mistakes. Mistakes are a beautiful thing. So we're going to say that our u is actually going to be 1 minus x squared. Because that way, whenever we take the derivative of this, the 1 is just going to drop out. So we get du is going to be negative 2x dx. The differential du is negative 2x times by the differential x. Alright. Well, now what we have to do is we have to spawn in -2 instead. So we get -2 and -1/2 on the outside. We're going to say that this is going to be -1/2 times by the integral, doing our substitution now, u to the power of 1/2. Our u is 1 minus x squared, so I just pulled out the radical and called it 1/2, times by our differential du. Integrating this now, we get -1/2 times by, we have to raise our power of the exponent by 1, so we get 3/2, and multiply by the reciprocal, so we get 2/3. Plus c. The 2's will cancel, so we get -1/3 u to the power of 3/2 plus c. Our u is 1 minus x squared. So plugging that in, we get this for our answer. Finally, for this last integral, I think this one is a small bit easier to see. What is the u and what is the du? This is our outside function here. This is the inside function. And then you can see that this is going to be the derivative of the inside function, except for it's missing a negative. So we're going to say our u is actually going to be cosine of x. So our du needs to be negative sine of x times by the differential dx. So now we can sub in our differential here and our u. So we get the negative, the integral of sine of u times by the differential du. Well, the integral of sine is actually going to be negative cosine. So we get cosine of u plus c. Our u is just cosine. So we get cosine of x plus c. That would be our answer. Alrighty, now let's talk about the substitution rule for definite integrals. Well, sometimes it's a bit easier to, rather than re-sub in our x's and stuff, we can just evaluate the function, or whatever we say our u to be, or our g of x at the points a and b on the bounds of the integral, and then use those to evaluate the integral of f of u. So really this looks like the integral from a to b of f of g of x times by g prime of x dx is equal to the integral from g of a to g of b of f of u du. So let's real quickly just work an example here, or actually several examples. So in this first problem, this one's actually a small bit more difficult, but we're going to say our u is going to be equal to x minus 1. Our du in this case is just going to be equal to dx, because the derivative of x is just 1, and we just have to multiply the dx over. But now what I want to do with this is we're going to sub the u in, so we get the square root of u. But we're now going to solve this x, or solve x for u. So we're going to get u plus 1 is equal to x. And now we're going to sub in u plus 1 for this x over here. So we get the integral, and I'm going to do the bounds in just one moment, of u plus 1 times by the square root of u du. Let's find out what the bounds are. Well, if we plug in the x value of 0, which is this lower bound, or sorry, the x value of 1, which is the lower bound, we'll get u of 0. And then now if we plug in 2, which is our upper bound, we get 1. Alright, well now what we have to do is we have to make this integral into a bit simpler of a form. And we can do that just by multiplying out the square root of u. So we get u to the power of 3/2 plus u to the power of 1/2. And it's the integral from 0 to 1 of du. Well, all we have to do is increase the power by 1. So we get 5/2. So times by 2/5. Plus 2/3 u to the power of 3/2. Plus c. And that would be our answer. Well, actually, not yet because we have to evaluate it. So now we're going to evaluate this from 1 to 2. We don't have to worry about the c, so I'm just going to get rid of it. Alright. Now let's think for a moment. What is going to be 2 raised to the 5th power? Or yeah, 2 raised to the 5th power. Well, it's going to be 2, 4, 8, 16, 32. So it's going to be 32 square rooted times by 2 divided by 5. Plus 2 cubed, which is going to be 8 square rooted times by 2/3 minus evaluated at 1, which is just going to be 2/5 minus 2/3. Now, of course, I can go through and simplify this. Am I going to? The answer to that question is no. I'm certain there's probably some simplification that's going to make it look pretty, but sometimes you have to think about time. Alright, now we want to do the integral from 0 to 1 of cosine of pi over 2 of t. Well, for this one, we want to set our u to be this inside function, the very clear and evident one, of pi over 2. So then our du in this case needs to be equal to pi over 2 dx. Do we have a pi over 2 in there? No, we do not, so we're going to add in a pi over 2. But we also have to multiply by its reciprocal to make sure it's still 1. So we're now going to get 2 divided by pi times by the integral from 0. And now let's solve for the bounds of the integral. If I plug in 0, it's still going to be 0. But if I plug in 1, the upper bound, it's going to be pi over 2. Alright, and we're evaluating cosine of u, du. So this is going to look like 2 pi times by the integral of cosine is sine of u, evaluated at pi over 2 and 0. Alright, so sine of pi over 2 is going to be 1. Sine of 0 is 0. So we get 2 over pi for our answer. Alrighty, well, that's all I have for you today. I hope you found this video informative, and if you did, please make sure you like and subscribe.